Hello and welcome to the SPIR-V Backend talk. We will discuss challenges of producing SPIR-V from LLVM IR. After a brief recap of key concepts, we will discuss technical problems of translating a semantically rich language using GlobalISel backend, proceed to real issue samples, and conclude with matters of stability and future work. Talking about stability, backend became a major project and a step in various toolchains, conformant with OpenCL, close to conformance with SYCL, DPC++. It's got better integration with external tools and libraries. Main progress is related to general logic of translation and overall stability, applicable to both compute and graphical flavors of SPIR-V, and it's not specific to any single vendor. The backend has a lot of new features, extensions, built-ins, intrinsics, but we focus now on how to be a GlobalISel backend for a higher level target, detached from any hardware. SPIR-V is an intermediate language for representing graphical shader stages and compute kernels. Its formal specification is driven by Khronos Group, and the backend is developed by Khronos member companies. The way to develop SPIR-V standard is by publishing an extension to a set of core rules. SPIR-V is a portable and stable cross-vendor program representation for a wide range of hardware, and it helps in the same way as LLVM IR, abstracting developers from vendor-specific instruction sets and front-end languages. The key challenge in mapping LLVM IR to SPIR-V is that both are higher-level representations. SPIR-V is inspired by IR, and it's a semantically rich language. Probably we should name the mapping translating to SPIR-V rather than SPIR-V instruction selection to make it evident that the task differs and not always obeys usual JSL translation scheme and machine verifier expectations. Another challenge is that SPIR-V doesn't represent any real hardware. It means to be portable, vendor, and hardware agnostic. The SPIR-V target, meaning behavior and properties, is just as abstract as the SPIR-V format itself. So we expect SPIR-V code to be translated later into an accelerated instruction set. As an option, it can be encoded back into LLVM IR. So we don't need register allocations, scheduling, and we defer hardware-dependent optimization. There is no formal semantic and a proof assistant to ensure translation correctness, but there is the Khronos SPIR-V eval tool to post-check that the code matches the specification. SPIR-V type system is rich. Model scope lists unique IDs of used types, constants, strings. Note that pointers are typed. Backend infers types in general and deduces pointee types in particular. Add to this complexity of inserting proper bitcasts. Also, LLVM code base is effectively banning usage of typed pointer type, even to passively keep pointee info between passes, and we use an extension type instead. Also, we'll mention subtle differences between semantics of statements and instructions. So first, a little context. Necessity and complexity of type inference are caused by difference between the concept of virtual register and SPIR-V ID, and the fact that low-level types cannot express SPIR-V types. VREX are still an abstraction, but they impose a vision of a hardware-dependent layer and restrictions on content and operations. This is a gap with the notion of SPIR-V ID, that is a higher-level concept referring to entities like object type and function. SPIR-V has a developed type system like other high-level languages, with composite types and applications leading to target extension types. Compare this to low-level types that are designed to machine instructions and low-level languages, where all complex is decomposed and reduced to a minimum info. To relate original IR types to final SPIR-V types, we employ two actions. Enrich IR types with annotations, tracing relations between IR values, deducing implicitly present types, and link IR values and GMIR explicitly, because Codagen doesn't keep track what VREC is related to which IR value. We look for known patterns to relate value and operand types, analyze composites and function call size, and revisit incomplete types after all functions were processed. Backend uses a global state to trace associations and introduces internal service intrinsics to preserve links between high-level aspect of code and its low-level representation. Aggregates lowering is a good demo for technical option solutions and trade-offs. So GlobalISel anticipates the advent of physical registers. SPIR-V has no instruction set architecture and expects that a single ID represents an aggregate, and it will not be disintegrated into low-level types. An aggregate argument gets flattened in IR translator, producing multiple VREX. It makes it impossible to translate a call. The initial approach is to remove aggregates so that a call is mutated to replace aggregates with I32. We record these changes and later restore a valid type. Drawbacks of this approach were revealed by SYCL test suites. It's impossible to deduce and store a correct type before IR translator due to omnipresent type I32. So to trace correct aggregate types, we use mutation info to get original function type during type inference. This doesn't eliminate the root cause. And arithmetic with overflow intrinsics is a good demo for the issue, because a code-gen pipeline may insert them later when the backend pass is not able to mutate the call, and they return a struct, not I32. IR translator has no special translation for backend intrinsics used to map IR values to VREX. A backend service call is an unknown intrinsic for IR translator. So when LLVM IDs get mapped into VREX, aggregates get flattened, producing multiple VREX, and such a call will not be translated. Even an explicit call failed in case of this intrinsic, either on attempt to mutate the call due to a wrong function signature, because expected result is struct, not I32, or if we don't rewrite the call, IR translator just gets multiple VREX and stops. So what options do we have? We could manually unfold intrinsics, translating them early into equivalent IR. That works, but ignores generic shared code. It's not the case when we wish to modify GlobalISel logic. We could employ a custom call lowering. It would overcomplicate solution, though, both in terms of development and maintenance. So our final option presents a much cheaper solution. We opt for improving existing approach. Backend utilizes LLVM fake use intrinsic to track the original IR value for the aggregates argument. This links a higher level vision of code with its low level representation. We also insert backend internal intrinsic to store in metadata a name and original type of IR value, otherwise it would be thrown away. The issue is resolved in this case, and we reused gen code logic, avoiding a burden of maintenance of target independent changes and an overhead of developing a custom call lowering. About control flow, like IR, SPIR-V also has models of functions, functions of basic block, etc. Unlike IR, several bullets, so GPU-specific compilers like to see CFG structure. Computational flavor figures this out, but shaders require structured control flow. Next is that it's commonly unexpected, but a label in SPIR-V, in fact, is an instruction, starting logical basic block. Also, it's not possible to delete instruction after the unconditional branch. It's the last instruction in a block by the spec. There is no instruction to encode if then, only if then else. So, as a result, we do not allow to restructure blocks as a branching optimization, like in branch folding if conversion, because it potentially breaks structured control flow, and anyway, it's hardly useful. Now we proceed to a brief demo from several recent PRs. The first is simple. Asm printer was hard-coded to ignore a possibility that a label concept, as it understands it, may be absent in a target. An intent to keep Asm printer agnostic about targets meant the fact that it always created a symbol for the end of function, if valid debug info is present. In this case, the solution is to check for a format and grant SPIR-V a right to differ. We check for the format, but in general, label concept is defined on the level of the target. More elaborated example is on the screen. So on the left, R1 and R2 are pointers, inferred as I8 and I32 types. IR has no explicit pointy type, but a chain of alloca returned from a function and assignment makes it possible to proceed with type inference. Below a line of phi node, types of the incoming R1 and R2 values must be the same. So on the right, in backend code, you see inserted a bit cast between assignment and the phi node. And that creates a problem. In LLVM, such a bit cast is a no-op instruction. It is not no-op for SPIR-V though. Without the bit cast, phi deals with inconsistent apparent types. So machine verify validates G underscore bitcast, and we see an error. Bitcast must change the type. Well, it does for SPIR-V, where we require a bitcast to change a PNT type. Given we cannot have optional restrictions on opcodes, we still could make it target dependent. Think of adding a virtual call to fine-tune the lowering process. Backend could implement its target lowering rule and override default invalid status of no-op bitcast. Meanwhile, all we may do is to choose a kind of an error to be invalid due to type mismatch in phi or using G underscore bitcast on pointers. Even more important example is about phi node. So op phi in SPIR-V is nothing else but a phi node. It starts a basic block, has pairs of incoming value and label per predecessor, etc. It has a difference that is subtle, not the point of this example. After instruction selection step, G underscore phi opcode becomes op phi. And machine verifier starts reporting VREC defs don't dominate all users. The problem is that traditional instruction sets do not implement phi instructions, but SPIR-V does. Possible solution could be that gen code doesn't hard code what is phi, but instead allows to override the check, introducing a check of kind of whether the instruction opcode represents a phi. We presented three cases where the first accepts that SPIR-V is different. In the second, machine verifier forces backend to fit into a scheme that is not feasible. A somewhat questionable way to fix without patching GSL is to generate op bitcast immediately without reusing G underscore bitcast. It would have an overhead to visit IR before translation and convert original bitcast to a call site. Also, in this case, we don't reuse shared code base and ignore existing bitcast opcode. So the third case questions the definition of instruction selection itself. In theory, instruction selection results in target-specific machine instructions, and SPIR-V is a boss. According to the spec, SPIR-V op phi implements the phi node in the SSI graph of a function, so it looks like an issue to report after instruction selection what the target specification considers valid.
Thank you, Slava. So first, let's take a moment to discuss some of the challenges associated with the transition to Opaque pointers in LLVM 17. While untyped pointers have simplified some aspects of LLVM IR, the transition has presented some very unique challenges for SPIR-V code generation in SPIR-V, and particularly in the case of the SPIR-V backend, pointer element types were not just used for emitting necessary type declarations, but also were essential in resolving OpenCL built-in types and function calls, retaining proper pointer casts, and finally in lowering nested types. Think of structs or arrays which are not flattened in SPIR-V. Now, without the explicit pointer type, SPIR-V backend has to deduce these types, and this must be done foremost correctly, and this early in the compilation pipeline. So recovering these types early is much easier. So to make sure we recover and retain the types, we have three passes working together at various code gen stages to work around GlobalISel lowering and flattening. So let's focus on the first one, SPIR-V emit intrinsics. The process of inferring types is logical, but nonlinear and often nested or recursive. First, types are deduced from common instructions such as gaps or stores. For each type assignment, the pass emits a target intrinsic, either SPIR-V assigned pointer type or assigned type in case of OpenCL or SPIR-V built-ins. Then the pass iterates over calls and adjusts operand types, emitting SPIR-V pointer cast intrinsic when a different type is expected inside of the called function. Following these, SPIR-V emit intrinsics pass tries to deduce types of remaining functions, and at the end revisits each instruction to fix any inconsistencies, or in other words, often just inject new pointer casts. Now keep in mind that this process is very complex and sometimes subjective. For instance, phi nodes may have incoming values with different pointer element types. When that happens, the most frequently occurring type is the one that gets assigned. Another thing is that some OpenCL or SPIR-V builtins have well-known or predefined types, and in these cases, the pass uses a lookup table with hard-coded values. Following both SPIR-V emit intrinsics and IR translator, we have a SPIR-V call lowering pass. In SPIR-V, type declarations or types are also referenced in the sequence of instructions defining a function. Hence, the pass tries to emit these sequences, and most of the times uses the types assigned using assigned type or assigned pointer type intrinsics. One exception is the case with OpenCL, GlobalISel, or really any SPIR-V built-in function call, where what we have in the module is just a stub. In these cases, the calls get demangled, parsed using a table gen file, the SPIR-V built-ins TD, and proper implementations, including the return and function parameter types, are emitted into the machine module. Following the two passes, at last we have the SPIR-V pre-legalizer pass running, as the name suggests, before legalization, which removes all assigned pointer type or assigned type intrinsics from the machine module and maps each machine IR register to relevant type. The mappings are stored in a global registry. This is to ensure that there are no duplicate type declarations, and each successive pass can use global registry to get existing or create new types. This is not just for pointers, but any types really. One important thing to note is that SPIR-V has a variety of types, such as optype image or optype event, which were previously represented as pointers to Opaque structs. In LLVM 16, a new target extension type, thanks to Joshua, was introduced to allow preserving these types while being, in a sense, ignored by target-independent optimizations. This is important for targets such as SPIR-V, but also DX and others, which require more complex own types in the code gen pipeline. However, there's a drawback. So these backends are now really incompatible with IR coming from older versions of LLVM due to the Opaque pointer transition. Another use case for target extension type is for representing nested types from the SPIR-V emit intrinsics pass, instead of relying on typed pointer type, as Slava said, which cannot be used for creating values. Lit tests were very helpful in the Opaque pointer transition, and as Slava noted, their number has significantly increased. We treat them as our most important and easiest way to debug or catch regressions. This is in contrast to external conformance test suite, which often rely on specific hardware or require dedicated driver stack. We have extended most of our lit tests with SPIR-V val lines, so the SPIR-V output of each test is piped into Khronos SPIR-V validation tool, which makes sure that the binary adheres to the specification. Also, Nathan has contributed a tool called SPIR-V Sim to test the currently developed SPIR-V structurizer pass. The tool focuses on control flow and cross-lane interactions, and most importantly is less fragile than simply file check lines. Of course, file check could still be used for these tests, but the order of check lines would need to always match the output of CFG, not the input IR. So this means that any contributor modifying these tests would need to be knowledgeable and make correct adjustments. So SPIR-V Sim helps us avoid kind of this ripple effect of changes which would affect the backend. SPIR-V Backend has changed a lot in the last 2 years, and in many aspects is a better alternative to the Khronos LLVM SPIR-V translator, often providing more concise or better performing code. So the next natural step is to establish the SPIR-V Backend as an official or non-experimental target. We will be following with this after the dev meeting. We are also looking to contribute SPIR-V consumer in the near future. Thank you very much, and we're open to the questions.
Thanks so much. That was a great talk. Any questions from the audience?
Hi. I was curious to ask, before opaque pointers, mean, the pointer types were never really reliable anyway, right? I mean, there was no guarantees that the underlying object was actually the type that the pointer type was saying it was, because we never made those guarantees in IR. So how did it ever work for you reliably, or was it more like just a heuristic that it was okay to be wrong sometimes?
So because there's not much difference in the level between SPIR-V and LLVM IR, I think in our case it worked pretty reliably. The one case which I can think of which didn't work at the beginning, or which required some adjustments, were in case of OpenCL kernel arguments, which often, as I said, were either just pointers to Opaque structs, but in some cases, often Open or Clang, when emitting OpenCL, LLVM IR just added the actual types into the metadata. So that's what we used to make those adjustments in the past, but that's the only case I can think of where this didn't work reliably. So I don't know if you have any additional example, we can talk a bit later. Yeah.
Have you spent much time thinking about the SPIR-V consumer case and how exactly it's going to share code with the existing SPIR-V backend?
So I think the easiest idea, we do not have any set idea on how to contribute to SPIR-V consumer. When I say SPIR-V consumer, I mean at least the SPIR-V reader part of the Kronos LLVM SPIR-V translator. So we would like to reuse as much of the code that already is in the translator repository. When it comes to reusing or sharing the code with the backend, one big thing is that we do have already all of the instruction definitions, all of the opcodes in our table gen files. So this kind of naturally would fit in and just wouldn't have to be repeated. I don't know if you have Slava any.
Yeah, I just wanted to say that it makes sense from purely software engineering perspective. So you have the same abstractions, etc.
Hi. I have a question regarding the structurizer. So, what's the future plan? Is it done, or what else needs to be?
So we are not working on a structurizer. It's mostly guys from Google, so you need to ask them. But it's in development. There is at least part of the structurizer pass already is in the LLVM repository. The one thing which kind of we need to focus on is how to test this reliably, because current lit tests with file check are not really a good way to test it. So we have this SPIR-V sim tool, but that's all that I really know about the structurizer.
And do you have is it discussed in the?
Yes, we do have the SPIR-V working group meetings every other week. Right now it's on Wednesday, so we do have Nathan and other people joining those meetings. So feel free to join and you can ask any question.
That's a part of contribution from Google folks and from Nathan, including this car, for example, about Op5. So
Yeah.
One more over here.
So you said OpenCL dumps type information in the metadata.
So as part of, in the past at least, I'm not sure if this was in one of the Kronos repositories, if it was in the LLVM repository. Before Clang fully supported OpenCL, this was one of the ideas, and this was how it was used. We had type information in the metadata, or at least for some types like the image or event. Yeah.
So that's something we are also exploring in the other dimension, whether because of the loss of types, information get lost. So I was just curious to know what is the extent of that, whether it also dumps the dimensions of the array, and it's not just the primitive types, but the derived types also.
Yeah, so this was a solution that was used, but I don't think it was a good solution. We struggled with this a lot. So one thing which Joshua proposed, which was this target extension type, this works reliably. And the issue with metadata is that any pass can just remove those, and we just don't have the type information anymore.
Thanks again for the great talk, and we're going to take just a 5-minute break to switch between sessions now, but the next talk will start in 5 minutes, so yeah, thanks.
Thank you.
Thank you.